Okay, I would like to welcome everyone to part 2 of developing ocean modeling capacity in Canada. Today we have, well, for the next period of time, we have 6 speakers. Please put any questions for the speakers in the chat, and we will get to those if we can at the end of the talk, and if not, the speakers can answer them there. So keeping us on time, I'd like to start. Qishuo Long will give the first talk on impacts of Arctic anticyclones on the freshwater content in the Beaufort Sea. Go ahead, Long.
Okay.
I have to stop sharing. Stop sharing. There we go.
See my screen?
Yes.
Okay.
We need presenter mode.
Presenter mode. Okay, today I'm going to talk about the impacts of Arctic cyclones on the freshwater content in the Beaufort Sea. So this work was supported by CSRF and MODCOM. First, I will talk a
Long,
little bit
we're not seeing presenter mode.
Sorry?
You're not seeing presenter mode and you didn't change slides.
Oh. Is okay now?
No, it hasn't changed yet.
Oh gosh. What happened?
Now we're seeing your view instead of the presenter view. We're just seeing your view, not the view. Can you switch screens?
Okay, switch screen. I stopped sharing that now, so I try it again.
Okay.
Can you see now?
We're seeing again your screen with the next slide showing and the notes. Can you switch screens?
Switch screen. How to switch screen? So
It should be somewhere on here as a choice. Maybe under display settings. Yeah, that one.
this one?
Yep, hit that one.
Okay. So it works now.
No, it didn't change.
It didn't
I
change.
don't know. Maybe we should go ahead just with this view.
Okay. So today I'm going to talk about the impacts of Arctic cyclone on the freshwater content in the Beaufort Sea. This work was supported by CSRF and MODCOM. So can you see this slide?
Yes, it changed slides.
Yeah. So now I will talk a little bit about why we did this work. If we look at the observations, we can see a significant freshwater accumulation in the Beaufort Sea because the Egmont convergence transports the surface freshwater to the Canada Basin. In recent decades, there's a sharp increase in the freshwater content from 2003 to 2022. So previous studies try to understand the freshening using the Beaufort High. It is a high pressure system in the Western Arctic. But the problem is, if we look at the change in the sea level pressure, we cannot see very significant signal. So in this study, we try to use alternative variable to understand the decadal variation of the freshwater content. in the Beaufort Sea. Because the observation, the data set is very limited, only lasts from 2003 to 2020. So we are going to use a numerical model to simulate the freshwater content in the Beaufort Sea. The model we are using is NEMO 3.6. We implemented the model NEMO for the whole Arctic Ocean. It has a quarter-degree horizontal resolution and 50 vertical levels. The river runoff is prescribed as climatology. Natural boundary conditions include PHC temperature and salinity, and the glorious ocean currents. The atmospheric surface forcing is JRA 55. So after 60 years spin up, we ran the model from 1958 to 2021. So in this study, we only focus on the data from 1960 to 2021. So the model has done a reasonable job to simulate the ocean salinity. If we look at the observation is on the right column, we can see a low salinity in the Western Arctic because Ekman convergence transports the fresh water into the region. On the Atlantic side is Atlantic water, the salinity is very high. The model can reproduce the spatial pattern, but a little bit underestimate the ocean salinity on the Atlantic side and a little bit of estimate the salinity in Canada Basin. But overall, it has done a reasonable job to simulate the ocean salinity. Here we have the cross section across this line. You can see, similar to the sea surface salinity, we can see low salinity in the in Canada Basin in Western Arctic Ocean, and high salinity on the Atlantic side. The model can reproduce this vertical structure because it can also reproduce the high gradient, salinity gradient at around 150 meters. The freshwater content is estimated from ocean salinity. So using this formula, the reference salinity is 34.8. If we look at the observation, this is average from 2003 to 2020. The data came from the Peterson. Again, there's a high freshwater content in the Beaufort Sea. The model can also reproduce the spatial pattern, but a little bit underestimate the maximum freshwater content. So next, we compute the average freshwater content of this red box. We got this time series. The red line is observations, black line is model simulation. So we can see, if we look at the observation, there's a sharp freshening from 2003 to 2020. The freshwater content increases from around 18 meter to about 20 meter in 2020. The model can reproduce this sharp this freshening, but a little bit underestimate the magnitude. Also, we can see the model can reasonably reproduce the interannual variation. So we can high freshwater content in this year, so also in the observation, low freshwater content. So overall, they can reproduce the spatial pattern of freshwater content as well as its variability. So next, I will talk about the impacts of anticyclones on the freshwater content. Here, the anticyclone is defined as a high pressure weather system with a time scale from 24 hours to several days. So first we use the sea level pressure to identify the anticyclones. Then we track the system and count the numbers. So we got this frequency climatology. So if we look at, so the data is GRA 55 sea level pressure. So we can see there's a maximum anticyclones in the area near Canadian archipelago, but in recent decades, there's a significant increase in anticyclones. The maximum increase is around 12. So that's almost double the climatology. So then we show the time series, the average anticyclone frequency in this area. That is the black line. The black line shows the anticyclone frequency. And the red line is annual freshwater content increase. So if the increase is positive, that means there's more freshwater transported into the Beaufort Sea. So if we look at the black line, you can see after 2000s, most of years has a high anticyclone frequency. So it's above the climatology. But at the same time, if we look at the freshwater content increase, the annual increase, also most of the years has a positive freshwater increase. So that's why after 2003, we can see sharp increase in freshwater content. The two lines are highly correlated. The correlation coefficient is around 0.51. That's quite significant for 62 years of data. So when there are more anticyclones in this area, so the freshwater content tends to increase in the Beaufort Sea.
2 minutes.
Yeah, 2 minutes. Okay. So next, I just want to say this increase is related to the change in the stratosphere. So we can see this is a temperature at 200 millibar. It's above 11 kilometers above the surface. We can see in recent decades we see significant cooling in the lower stratosphere. If we look at the cross section, we can see cooling in stratosphere and warming in troposphere. If the air becomes cooler, so the air becomes denser, so the air pressure tends to increase. So this can be shown using the geopotential height. We can see, so consistent with the cooling in this area, we see high pressure system in the low stratosphere. This high pressure system go all the way to the surface. So that's why we can see more anticyclone in this area. I just skip this one. So why there's a cooling in stratosphere? So I think there are two mechanisms. One is increased greenhouse gases. So when there are more greenhouse gases in the air, so the long wave radiation is trapped in the troposphere, and the stratosphere gets less heat, so it becomes cooler. The other mechanism is the depletion of ozone. So if we look at the ozone concentration, we can see sharp decrease from 1980s. So when there is less ozone concentration, so the air absorbed less solar radiation, it also becomes cooler. So this is two mechanisms for the cooling in stratosphere. So in summary, the LIMO can reproduce the ocean salinity, freshwater content, and its variability. The freshening in the Beaufort Sea is well correlated with the increased anticyclone frequency in the region. The enhanced anticyclone activity in the Western Arctic is associated with a cooling in the stratosphere. The increased greenhouse gases and the depletion of ozone are responsible for the cooling in the stratosphere. That's it.
Thank you very much. We have one question already in the chat.
Yeah.
How do the cyclones lead to Beaufort Gyre freshwater content increase? Is it
Yeah.
purely through local effects, or is there also impacts on the Bering Strait inflow?
When there are more cyclones, so the surface wind become more anticyclonic. So that's why it can affect the freshwater content through the Ekman convergence. So more fresh water would be transported into the Canada basin. So that's why we can see more freshwater content in recent decades.
Thank you. Moving on to our next talk. Our next talk is by Anna Eras, and she's going to tell us about a year-round perspective on marine physical dynamics and sea ice in Jones Sound, Nunavut, based on observations and model. Go ahead and share your slides.
Hello?
That
That
looks
okay?
good, Anna.
Okay,
Thank you.
perfect. Thank you. So good morning, everyone. My name is Anna, and I'm a second PhD student at the University of Alberta, and I work with Paul Myers. I'm part of the Ice to Ocean project, which is a community-based project in the Canadian High Arctic. And personally, my research is focused on understanding the marine physical dynamics in Jones Sound. And in this talk, I'll be showing comparisons of our model simulation and our observational data. Okay, first of all, just to give a quick background, due to the thermohaline circulation, the water column structure in the Arctic Ocean is stratified, having a seasonal surface layer followed by a Pacific water layer that enters the region through Nares Strait, and the warmer and saltier Atlantic layer on the bottom that arrives through David Strait. And my work is going to be focused in the Canadian High Arctic, specifically in the south of Ellesmere Island in Grise Fjord. That is also home of the Inuit Hamlet Institute that are our partners in this project. So thanks to our collaboration with the community of Grise Fjord, we already have collected 445 CTD profiles since 2019 that are represented as the yellow dots in the map. We also have an historical CTD dataset since 1926 that are the blue dots. So with these CTD profiles can help in giving insights into the different water masses, but it doesn't tell us much about the annual processes. So that's why we also install a mooring, an oceanographic mooring at Belcher Bay that is just south of Jones Sound. And with this mooring, we obtain mainly temperature and salinity records at different depths through the water column during a year, from August 21 to August 22. A part of that, we also have a model dataset, and we use the oceanographic model NEMO that I think we all know. And depending on the simulation, we use the version 3.6 at a quarter degree of resolution. And in the configuration ANA 4, that is for the Arctic and Northern Hemisphere Atlantic. This gives us a resolution at 12 kilometers of horizontal resolution in Jones Sound, the region that I'm studying. And depending on the simulation, it can be coupled with two different sea ice modules, LIM2 or LIM3, and it can be forced with different atmospheric forcing like CGRF or ERA5, and different initial conditions. So when we are running a model, we end up having a lot of different simulations depending on the configuration that we are using. And this brings me to my first question, which is which simulation fits better the CTD observation in Jones Sound? And to answer this, I'm going to use the CTD dataset that I just mentioned. So for each CTD profile that we have, I'm going to select in the model output the closest grid cell for the closest time, and I'm going to compare them. And for the moment, I'll be focusing in temperature and salinity. So for the model output, I've chosen these two simulations. The main difference between them are the atmospheric forcing. One is CGRF and the other ERA5. The CI's model is also different. One is LIM2 and the other LIM3. But the main difference is the initial condition. One of the simulation has GLORIS 2v3, that is a reanalyzed product of a quarter-degree resolution. And the new one, we are using GLORIS 12v1, and it has a 12-degree of resolution. So from now, I'm going to be referring to these two simulations as low resolution initial condition and high resolution. So taking a look first to the initial condition at 2012, that is when our simulation starts. Here we have TS diagrams for 6 specific locations at Baffin Bay, and we are comparing in blue the observations, and in red the initial condition. And we have the same with the high resolution initial condition, and we can actually observe that it fits much better the simulation, the observation. But I would like to quantify how important this could be to our simulation. So starting with the comparison, here we have TS diagrams with the CTD data color in the green scale and the NEMO data color in the gray scale. In the plot of the right, that is the low resolution initial condition, we can actually observe that in the lower layers, we have the denser and cold, warmer Atlantic water, and it's too warm compared to the observation, whereas in the high resolution one, it looks also warmer, but it looks a constant offset through the whole water column, and this could be, for example, easier fixed or taken into account. So in the same data, but in vertical profiles, here we have the CDD in white, in blue the low resolution initial condition, and in purple the high resolution one, salinity and temperature. So for example, if we check the temperature, as I mentioned at the beginning, we can clearly distinguish the two layers. The Pacific one, the colder, and the warmer, the Atlantic. So we can calculate the mean temperature of each one. With that, with this mean temperature value, we can calculate the delta T, that is going to be the temperature of the model minus the temperature of the CTD for each point. And we can obtain this kind of comparison. For example, for the polar water, here we can actually see how the high resolution, that is the purple, approaches well, is around 0 almost for all the years, and the observations, and how the low resolution one, that is the blue, it looks underestimating the observation at the beginning, and after it becomes a bit more accurate. If we do the same for the Atlantic water, we observe a similar behavior. The high resolution has a constant offset during the whole time, and the low resolution is underestimating at the beginning, and after overestimating the temperature of the Atlantic water. So this could maybe be understood as the spin-up time of the model, and it started in 2002, so until 2015 is a lot of years. So from a more general point of view, here I'm showing the temperature of the Atlantic water at 320 meters depth for both simulations. And we can actually observe the cyclonic circulation around Baffin Bay. But also we can, and mainly in this one, the low resolution one, we can actually observe how it takes a long time for the Atlantic water to flow from the North Atlantic and reach Nader Strait. Is in here, for example, we are already in 2010, and we can actually see how the Atlantic water is not still fully in Old Baffin Bay, whereas in the high resolution one, we observe it, right? So from now, we have seen that initial condition plays a key role in the temperature and the salinity simulation. being the new round with high resolution significantly more consistent with the observation. And following this, the spin-up time is it could be reduced from 12 years using low resolution to 5 years using the new high resolution glories. So for now, I've checked temperature and salinity, but what about dynamical processes? So for that, I'm going to use the mooring data. As a reminder, the mooring was located at Belcher Bay, that is south to the Jones Sound there in the map. So here I'm showing the temperature and salinity records during the year. And the red line is just the sea ice concentration data from satellite image. So we can observe different processes. For example, the change in stratification being in summer more stratified with a warmer surface layer. The sea ice formation was at the beginning of November, and we can actually observe how after that moment we start here in the salinity, the brine rejection. So the upper layers became saltier and they became heavier, so they start to sink. And that came with the deepening of the mixed layer and it reaches around 150 meters in the middle of the winter. So this is from the observation. And now I'm gonna compare them with this true simulation of the model. So for the salinity, if we compare it with the salinity, we can actually see that the process is well represented. However, the high resolution one, it shows a stronger stratification and a shallower brine rejection. So that could lead to a shallower mixed layer. And actually, if we check this temperature, we have the same result. The mixed layer depth goes until 80 or 100 meters in the high resolution one, that it's shallower than in the observation, whereas the low resolution one looks representing better this deepening of the mixed layer. And one of the hypotheses is that this could be related with the sea ice. So if we go back in time 4 years, we actually observe a similar pattern. So deeper mixed layer, like the mixed layer is deeper for the low resolution, and it corresponds with a smaller sea ice concentration normally over the year, and that could actually allow us to more wind stress and this the surface and more mixing and maybe more upwelling. And another important fact is that we actually in the low resolution one we observe also more fluctuation in the deeper layers, all of these entries of warm water that are not represented in the high resolution Y. So that could also be related with the larger sea ice cover. And just to finish, checking quickly the sea ice. Here we can actually see the sea ice fraction, and we can actually see that the is higher in the high resolution one. And this, if we check the sea ice thickness, we actually observe that the low resolution one has a thicker sea ice. So that could also be in agreement with the higher brine projection that we observe. So just to finish, the take-home message is that the representation of the mixed layer depth seasonal cycle looks directly related with the sea ice simulation and the stratification of the water column. That means that weaker aligned stratification leads to an increased mixed layer depth. That a good representation of the sea ice concentration and the wind forcing allows to better represent the deep layers dynamics and possibly Atlantic water upwellings and mixing. And the initial condition closer to the observation could significantly reduce spin-up time. And that's it. Thank you.
Thank you, Anna. We already have one question in the chat. Anna, since you used the GLORAS 2 product, why did you also use the full set of CMEMS GREP, multi-system ensemble analysis, to see how different low-resolution systems differed in their analysis fields?
So I'm trying to read the... why did you also use the full set? the question is why I'm not using that, or?
Yes, I'm sorry, I forgot.
Okay, sorry. My God. Yes, that could be actually an idea. For the moment, I've been using that because we have our simulations run with that. So I'm working with the outputs, but that could be actually a great idea.
Thank you.
Thank you.
Okay.
I'm still
Our next speaker is Sarah MacDermid, who's going to talk about Canada's three oceans, multi-decade ocean sea ice hindcast, a Hudson's Bay sea ice study.
Okay, so you can all hear me okay?
Yes.
Perfect. Okay. Well, we are. I'm sorry?
Can you share your screen?
I thought I was. Back. There we go. How are we doing now?
Zoom is thinking about it. There we go. It's not in presenter mode, but we can see your screen now.
Give it a second.
There
I
we
think it's
go. Looks
delayed.
great.
All right. Okay, so I'm going to present to you a project we've been working on at DFO. This was a project for a CSRF project within the DFO funding pools. I'm currently back at my substantive position in Environment Canada, but this work was done while I was being used by DFO for a period of a year and a half, and it's a very good project. So I'll give it a little summary for you all. The project motivation, basically, it's a CSRF project, 3 years. So we're running into year 3 now. So we're amalgamating all of our wonderful data and getting it in high gear now. Basically, the project is a high resolution climate simulation for Canada's 3 oceans. On the right here, you see the coverage of the domain. So the simulation will run from 1958 to present with ERA 5 forcing. Already 50 members have been identified as interested partners for the model simulation. It's also a project hosted by the Supreme Group of the UN Decade Ocean Science for Sustainable Development. This is our model and domain. It's NEMO 36 with LIM 3. We've extended the southern boundary to 7 degrees north and the Pacific boundary to 45 degrees north, 75 vertical levels. The project is going to be run with a 12th of degree model, but everything I'm going to show to you today are results from a 1/4 degree simulation. As you all probably know, the 12th of a degree is a beast to run on supercomputers. So the 1/4 degree setup is ideal for testing and simulating and getting things tuned up. So the ocean forcing comes from ORAS 5, the 3D initial conditions and open boundary conditions. Our model uses 5 constituents of tides. We don't bother over-tuning these. We just wanted to make sure that the amplitudes were good and the phases were not bad, but we didn't want to spend any time over-tuning those tides because it's a climate simulation. So we just wanted to make sure that the tidal mixing was good enough. It's forced with runoff from 421 rivers. That's for the 12th degree model. There's a slight differences with the 1/4 degree model, but it's monthly varying and spread when needed. The Greenland ice melt comes from Paul Myers' ANA 4 domain, 1/4 degree. The 12th degree model will use the higher resolution output. Thanks, Paul. So the atmospheric forcing we're using is from ERA 5, so it's a 1/4 degree global reanalysis. Everybody knows, it's well documented that the wintertime air temperature over sea ice is too warm. This is a picture describing or basically comparing the DFS forcing, which has been tuned with observations over ice to get a better representation. And so taking the difference, you can really see where that the bias in the ERA 5 pops out, but we use the forcing nonetheless. And in order to deal with the bias in the forcing, we basically we tune the model very crudely. It's very not realistic, and we understand that, but we really wanted to do the ERA 5 forcing. So by tuning the snow conductivity outside the normal range, the default being 0.31 watts per meter per Kelvin, and we increase it over October and March to increase the transfer of heat from the ice through the snow into the atmosphere, which increases the growing of the ice over the winter period. And over the period April to September, we decrease it so that our ice lasts longer, because we have a problem with ERA 5 melting too quickly in the summer and not growing enough in the winter. Another parameter we tuned specifically for the simulation was the bare puddled ice albedo. So this really only affects ice during the spring melt period. And so we increased the albedo to slow down the melting. And on the right-hand side, you can see our little simulation we did from 1994 to 2005 that really shows the effects of bringing our ERA 5 simulation monthly mean sea ice area for September up to the same level as other models. We ran a couple of simulations with changing only these parameters in ERA and comparing with the other forced simulated sea ice. And basically in March, it's not that much of a difference, but all models are basically under the same values for the period. So when we went back and started from the beginning in 1958, 1957, at the end of 1957, we basically ran a 60-year simulation with the September sea ice area shown here. And in black is the OCSAP observations for total North American sea ice area. And it's not perfect. Models aren't perfect. We have no data assimilation in our model. So this is actually quite good. And we are happy with that. So now moving on to the Hudson's Bay area, here is basically a monthly picture of what happens at Hudson's Bay. In red there for on top being observations, in the middle being our simulation, and the difference on the bottom, you can see as an understanding of Hudson's Bay, in the winter it's fully covered, in the summer it's fully open, and you can see the transition in between, and we do see basically the same thing happening in both model and observations. So looking at the phenology instead, looking at the freeze-up dates between 1969 and 1998, Environment Canada has this wonderful atlas of sea ice where it describes the first day with at least 50% ice concentration and the last day on the right. And basically our model on the top is really well simulating the freeze up, the progression of the ice as it freezes up along the coasts of Canada and Hudson's Bay there. Our freeze up date is quite reasonable. Our breakup date, not so much. We're still looking into that. But I'll just concentrate on the freeze up date today because 10 minutes is not a lot of time. So looking at the Hudson's Bay trends in sea ice phenology, on the left there, I have a paper from Gagnon and Gao. I'm sorry, I'm probably butchering names here, but from 2005, which basically showed that the trends in sea ice in Hudson's Bay between 1971 and 2003, based on observations, there was significant trends in the northern parts of Hudson's Bay that showed like basically 5 days per decade of less sea ice. And so our model basically shows that same ice freeze up trend from 1971 to 2003. The dots there correspond to the p-value or the statistical significance of the trends that were calculated in the model. And we do show the same, roughly the same values of 0.4 to 0.6 days per year. But if we look at the ice freeze up trends over the whole period of our model, the trend is much, much weaker. So that's, I mean, good in a way. We're not showing the same alarming trend here, and I'll go into a little bit what's happening over the long period. So when we look at the whole time period, this is basically just the ice freeze up dates for the central Hudson's Bay region. Between the early part of the period from 1960 to 1995, basically, we have a very steady, stable system. And then something happens in the middle of the 1990s, and there seems to be some kind of regime shift that the ice freeze update is later, is about a week later. we did basically a signal analysis of this to produce this graph to show where the change point was located, and doing a little bit of a research into the papers that were available. This is not actually new at all. Back in 2010, the late Hochheim and Barber identified this exact issue in the Hudson's Bay region that shows basically a trend in surface air temperatures around Hudson's Bay, leading to a regime shift also in the mid-90s. So what they did was they did a huge analysis of the surface air temperature, did some correlation studies, and it seems like the East Pacific, North Pacific pattern and the North Atlantic Oscillation, a lot of these teleconnections also had some kind of shift in the mid-90s to explain some of the changes in the sea ice. And I don't have, here we go. So basically showing what I showed in the previous slide of the trend being not so bad. So if we do a total trend analysis over the whole period, the trend is a lot less steep than the trend if we just looked at the same period of 1970 to 2003, which shows a very alarming trend, which is no longer the case. So if we look, sure, thanks. If we look at the results before and after this regime shift, basically we see no significant trends in the ice freeze up. So in 1958 to 1995, it even looks like there's a negative trend over the central Hudson's Bay, but again, it's not significant in our models. And post 1995, we have again some slightly less or negative trends in sea ice freeze up dates, with a little bit of significance over the central area. But that's not to say it's not alarming. If we look at the difference between those two dates, we get a week to 2 weeks over this region in difference in ice freeze up. So there's definitely a change. It just seems like this system here, we'll have to look into it further, is quite stable. But when it's pushed enough, it seems to have made itself a new stable pattern. But 1 week to 2 weeks earlier or later in ice freeze up in the region. That's actually it. That's all I have today. I wanted to thank all of my collaborators and co-authors. This is a big project, and it's very exciting. We're about ready to start releasing the Kraken of our 12th degree model. We're just trying to decide our spin-up strategy for the next set of simulations. We're still going to analyze the 1/4 outputs because they're actually quite useful. 25 years, or sorry, 60-year simulation is quite useful. So we're finalizing the strategy. We're going to release our 60-year 1/12 degree run, and hopefully we'll be able to share it next year at CMOS. That's it.
Thank you very much, Sarah. At this point, there are no questions in the chat, so I get to ask my question. Have you any idea why you see this delta change? What nonlinearity causes it want to go from one to the other so strongly?
You know, I have no idea. This is the last thing I looked at before moving to EC, and it would be an amazing study to do. Yeah, I have no idea. It just seems like a stable system, and then all of a sudden it just got pushed over the edge.
Okay, I have another question. This is from David Greenberg.
Yeah.
Earlier modeling efforts in Hudson Bay found that they were hampered by lousy bathymetry in Fox Basin, even affecting the driving of North Atlantic tides. NONA is largely absent and IBCAO is interpolated from insufficient data. Have you found any better sources of bathymetry in Fox Basin?
I am no expert in bathymetry. I know that Xiamen was looking at these details in bathymetry in Baffin Bay exactly like last week. So he's taking over this project, and hopefully he'll have some insight into that.
Okay, thanks, Sarah. And I guess we can move on to our next speaker. So our next speaker is Pouneh Hoshyar, who's going to talk about exploring Western Labrador sea dynamics for ocean and climate implications. So Interesting. Okay.
Okay, can you see my screen and hear me well?
Yes, Pouneh, we can see the screen. It's in correct mode and we can see you and we can hear you.
Awesome. Hello, everyone. I'm Pouneh. Pouneh Hoshyar. I'm doing my PhD with Professor Myers at the University of Alberta. My PhD research mainly focuses on very high resolution modeling of Labrador Sea. In this talk, I will present some preliminary results of Labrador Current's dynamics like eddy kinetic energy and its associated instabilities using a very high resolution configurations of NEMO ocean model. Okay. Labrador Sea is located between Greenland and Labrador, Canada. The Labrador Basin is affected by multiple currents. Okay, we have cold and fresh East Greenland Current and warm and salty Imminga Current. These will form West Greenland Current, which follows cyclonically into the Labrador Sea and also going to Baffin Bay, moving and living it southward. We have outflow from Arctic through Davis Strait and Hudson Strait. They all form by Labrador currents, leaving the Labrador Sea. We also have Deep Western Boundary Current, which follows into the Labrador Sea at depths. So what's the motivation to explore the Labrador Sea? Labrador Sea is one of the unique areas that we have convection process and formation of Labrador Sea water, like mood waters. We have like gas exchanges in this area, circulation of subpolar gyre ventilation. These water masses will feed the Atlantic Meridional Overturning Circulation, or EMOC. Also, Labrador Sea is characterized by a dynamic influence of oceanic eddies. These eddies will play a critical role in modulating its circulation pattern, preconditioning for like convection process or recertification of this area, and also driving exchanges into the Labrador Sea interior. So it's an important region to investigate. And here you can see the configurations of NEMO, some of that you may see in the ANA 4 Arctic Northern Hemisphere Atlantic 1/4 resolution in some of our people in the lab presentations like Taya and Anna. This one is ANA 12, 1/12, and here it's our high resolution model configuration. ANA 4 is VG12 Lab 60, the parent is like 1/4. The firstness is like 1/12, and the innerness is 1/60 with overall resolution of 1 kilometer over the Labrador Sea. So I'm using these configurations, mainly working on the high resolution configuration, and this ocean model is coupled with a LIN2 sea ice model. Okay, let's see what's going on into the Labrador Sea. For this, I put 3 movies of vorticity on the left, in the middle mixed layer depths, and on the right is convective resistance. In the vorticity movie, we can follow the eddies, which is shedding from like West Greenland Current, Imminga rings. They follow mostly in the northern Labrador Sea, and some of them can reach into the Labrador Sea interior. We also can see the eddies shedding from the Labrador Current. You can see 2 branches of Labrador Current. Here we have like mixed layer depth, which reached its maximum value in winter, particularly in March. And on the right, we have convective resistance moving. The convective resistance is defined of the measure of the amount of energy which is required to remove stratification from column of water to have mixed layer in that area. So for the regions that we have higher values of convective resistance, it suggests that we have a strongly certified column of water. As you can see here, in the areas that we have the eddies from like boundary current eddies and Imminga rings, we have high values of convective resistance. So it shows that these eddies keep this area strongly certified. Okay. Let's see how convective resistance and mixed layer depth change with varying model resolution, like our low resolution models to our high resolution. On ANA 4, which is our 1/4 model, we can see in this plot on the left that we have much lower values of convective resistance compared to our high resolution model, which we can see much higher values of convective resistance all over the Labrador Sea, especially in the northern Labrador Sea, where we could capture the eddies well. And what happens to mixed layer depths? So for UNO4, we can see we have much broader and deeper mixed layer compared to our Lab 60, which is our high resolution model. If you go through the Pouneh et al. 2020, you can see how well this Lab 60 could estimate the mixed layer depths with observations, Argo observations. So we can see by switching from low resolution model to our high resolution model, the estimation of mixed layer depths and also the process into Labrador Sea improved. This says that our high resolution model, because it's eddy rich, is able to resolve eddies. These eddies are responsible to certify the Labrador Sea, especially north of the Labrador Sea. So we can get more realistic results and estimations of mixed layer depths and other processes, which highlight the crucial role of small scale features in a model. So in my research, I would like to do eddy analysis linked to the western side of the Labrador Sea, the area that I showed with like solid red line here. That's because we've already done a detailed analysis on West Greenland current side, this side, because of its importance on stratification and water mass formation into the Labrador Sea. So I would like to do analysis on this side. And the other thing is that we relatively have a limited knowledge on boundary current eddies shed from Labrador Current. Also, previous studies using low resolution models, like one of the studies that I put the results here, which uses 1/12 model, suggested that the eddies shed from the Labrador current appear to exert only minor influence on preconditioning and recertification and have a little exchange to the Labrador Sea interior. As you can see in these plots, the bars, the green and blue one, belongs to northern Labrador coast and southern Labrador coast, mostly liquid freshwater transport. And if we check, we can see that there are only limited exchange with Labrador Sea interior. So we would like to see, by switching to 1/60°, how the idea of little exchange with Labrador Sea interior will change, or if Labrador Current just doesn't have that much exchange with Labrador Sea interior. The other things that I would like to investigate in my research is to investigate how to Labrador Current instability contribute to eddy formation in the region, and how the Labrador Current's instabilities vary seasonally and interannually, and also how do eddies and instabilities of Labrador Current impact the stratification in the Labrador Sea. I won't go through the math here, but it's how we are calculating the eddy kinetic energy and for like estimating the contribution of Barr-Culling and barotropic instabilities in like EKE generation. We are using the energy transfer terms, which are available here. I won't go through the math again. And here you can see preliminary results of eddy kinetic energy for like average top 100 meter over 2008 to 2018. You can see two branches of Labrador Current here. The seasonal variability in EKE corresponds to sea ice variability, showing less EKE during periods of sea ice cover. And in the middle and on the right, we have Barr-Culling and barotropic seasonal variability. Positive values suggest indicating the eddy formation and negative eddy attenuation. We can see lots of negative values for Barr-Culling instability in these figures, which suggest the reduced eddy activity and limited and consequence in like limited exchange into the Labrador Sea interior, supported by previous studies. However, we can still see some positive values, the red ones, which shows that eddy formation is still occurring due to these instabilities. And here you can see the section analysis across AR7 West. On the left side, we have volcanic instability average over 2008 to 2017. And on the right, we have barotropic instability. We can see based on the left figure that volcanic instability is mostly important for top 1000 meter, and barotropic instability is also important for deep western boundary current, which circulates into the Labrador Sea at depths. Okay, again, these are some preliminary results that I got. And thank you so much. Please let me know if you have any questions or suggestions.
Thank you very much, Pouneh. I'm not yet seeing a question in the chat, so I get to ask the first question. And so there have been a number of studies on the Labrador Sea Current, including glider studies. Are there any there that will help with your evaluation?
For like evaluating the instability results? Yeah, there are some. Actually, there is RIC 2019 that they have done like some analysis on like Labrador Current side as well. So they would be helpful to do like for validation. And we are also interested to do the same with like observations to see how the can we compare with those two.
Okay. And now we do have a question from the chat. The question's from you, Lou. For eddy exchange, both heat and fresh water, how different is the West Greenland Shelf and the Labrador Sea?
And Labrador Current, I guess.
I think so, yeah.
West Greenland Current, it's more stronger compared to Labrador Current. And if there is in our lab, people have done like some analysis on like West Greenland Current, and they saw like lots of exchanges through the western side of the Labrador Sea compared to eastern side. So I haven't done the freshwater fluxes and like heat fluxes yet for like only this side. I've done for like the whole Labrador Sea in another project that I was working to see how much of these offshore exchanges happening with Labrador Sea interior. And the exchanges, it's not like that much compared to like if we only consider the western side. Western side has more significant impact, as you saw in these movies. The eddies shedding from like the boundary current eddies on the like western side could even reach to inside of the Labrador Sea part of it. But Labrador Current one, I don't know why it cannot play it now. Is it playing? Oh, I don't know why it's not working now.
So you use clarifying his question. Yes. So you use clarifying his question, and this is probably the perfect plot to have up. How does the eddy exchange between the West Greenland Shelf and the Labrador Sea vary between different models?
I haven't done it. I'm just working on this Lab 60 configuration, very high resolution. I haven't done it yet. But our this Lab 60 configuration, it's able to capture most of the eddies, while the others cannot do that, and they don't have the eddy parameterization that we have. Actually, we have some other experiments in our group that they include eddy parameterizations like SMLEs to include the effect of these eddies. But the experiments that I've showed here for like the convective resistance and mixed layer depths ones, they don't include the eddy parameterization, and they cannot capture eddies well. That's why they have like these weaknesses in like estimations for mixed layer depths or like the process like convective resistance and convection stuff.
Thank you very much, Pouneh. Let's move on to our next speaker at this point. So our next speaker is Paul Myers, and he is going to talk about freshwater exchange from the Labrador Current into the subpolar North Atlantic.
Okay, thank you. I assume you can see my slide?
I can see your slides and I
So
can.
yeah, I'm going to continue on the track Pouneh was looking at with exchange from the Labrador Current versus the Wesley Current and freshwater issues, given that we know questions of as more high latitude melt occurs, more Greenland melt, what happens with that fresh water and will it affect water formation in the Labrador Sea? AMOC questions like this. So this is an outline I'm going to focus on again on the 160-degree nest, comparing with observations on the Labrador Shelf, and then talk about some of the exchange processes. And as I was saying, there's questions about, does the changes from the linkage with the Arctic lead to fresh water, more fresh water coming in the boundary currents? Is it getting out of the boundary currents? If so, where? What is the impact on stratification, water formation, overturning, etc.? And we've been trying to get the mesoscale involved, even potentially parts of the submesoscale, and get those eddies that are important in all the stratification and exchange processes. We want resolutions going down to approximating 1 kilometer. So we've been running this triple agrif nest or double agrif nest to get us down to the 1/60th in the Labrador Sea. I liked how Sarah said 1/12 is painful to run, and well, since we're running 1/12, I agree, but wait till you go to 1/60th, and then the computer costs do get somewhat insane. But anyways, it's fun to look at when you finally do get results. And the advantage is, as you can see, looking at the number of Rossby radius deformation radii per grid cell, for the most part, except on a little bit to the shelves and the Grand Banks, 160 is enough to allow us to have multiple grid cells per deformation radii that at least represent a reasonably good spectrum of the eddies. Looking at the fresh water, this is animations. Just look at the panel on the left here. It's the freshwater content relative to 34.8. You can see, again, lots of fresh water on both the West Greenland Shelf, which has the greater exchange with the interior, and then all the fresh water coming out of Baffin Bay, connections with Hudson Bay coming down the Labrador Shelf. There's eddies in that, as Pouneh was talking about, but not necessarily lots of exchanges into the interior from the shelf. But there is interesting behavior of the coastal and inshore current, and then farther south around the Grand Banks, Flemish Pass region, there seems to be tremendous amounts of that fresh water getting offshore and getting into the gyre, and then what's happening there. And especially the velocity structure, so this is just the magnitude of the velocity. The thing you get, as well as the eddies, is you can really start to see the inshore coastal component of the Labrador Current, just as with the West and East Greenland Current, that's also playing a role in this places where there's exchange between the currents, strong then flow on the coastal current before then getting offshore. And so trying to explore, what does this all say about the transport, where the fresh water goes, and does a lot of it then miss the convection side and get taken up in more the subpolar front region, the North Atlantic Current region of the North Atlantic. The model's also got sea ice. The only thing I'm just showing here is the sea ice response. If we compare sort of the black curve, and then the red is based on satellite. I got to wait till the next year. But the model and the ice fields from the model and the observations are realistic. There's not excessive sea ice in the model. It's not flooding into the Labrador Sea. And so it's not really a major contributor in the freshwater budget compared to the Labrador Current compared to the liquid freshwater component. Comparing, we use DFO's Atlantic Zonal Monitoring Section, 7 sections, taken up to 3 times a year across the shelf. And they go into the deeper water as well as covering the coastal. And so we compare velocities. We take the TS data, use thermal wind for baroclinic geostrophic. Then I get a barotropic velocity from the GLORIS reanalysis as my correction. I don't put variability in that because I want the variability to come from the TS. You look at the variability structure of that data, do a Monte Carlo analysis to get error bars. So again, we have something to evaluate the model. So to start off with what's normally one of the hardest comparisons for a model, TS plots. So we use our Lab 60 and the AZNMP. And when I first plotted this, or the student who was working on this, Elena's plotted this, I was amazed. I've rarely seen models and observations actually agree that much. There's definitely some offsets as we go farther south along the shelf, but I think for the most part, this does say the main water masses are being represented in the high resolution signature. The resolution allows us, we have our main shelf break current, but we also get, as we go south, we also have that inshore component of the Labrador Current represented in the model. There's a lot of variabilities between the months, wind strong, especially in sort of the winter season, weaker in summer. There's also a lot of interannual variability with time, which I'll come back to when I get to the transports. So here, and I want to be careful. So here I've looked at the salinity anomaly and the potential temperature anomaly in the model inshore of a given isohaline. In this case, the 33 isohaline, and that's picked because it's fully included in the model. And what you can see, the temperature's got a lot of higher frequency variability, warm and cold years, but in general, the fresh water in the Labrador Current has gone from saltier to fresher with fairly significant size of anomalies. The other thing that's important to see is the color is sliding offshore. So the area that's got fresh water is going more and more across the shelf and even across the shelf break. So there's a wider area enclosed in Gehring's isohalines. And in fact, this is what I've got here, the 7 sections north to south. The red is the oldest, to the black is the newest. And this is, again, as I said, the 33.3 isohaline. That's the one that's completely included in these observational sections. So I picked the same one with the model. And you can see very clearly the freshwater wedge is moved, in some cases, several hundred kilometers offshore over a decade. So obviously you've got a lot more low salinity water than associated with changes in the velocity, leading to significant increases in the freshwater transports. We've estimated then the mean transports. With Lab 60 of the model, the AZMP are from the observations based upon thermal wind and our barotropic correction from GLORAS 12. And I don't have the error bars here just because of space in the table. Thing that surprised me is, or not surprised, but is nice that the observations, model and observations, generally agree very well. I've used 2 different definitions of isotherm and fresh water. So we can look at more the coastal component and the full Labrador Current, and you can see fairly significant numbers. And especially if you look with respect to 34.8, which is the typical Arctic one, you see numbers that are generally much larger than in some of the other estimates, especially in the past, that I think are suggesting there's more fresh water coming out of the Arctic, coming off Greenland, and going south in the Labrador Current. There's a strong seasonal cycle in that transport. I think for time, I'm not going to say more. We look at, again, that's 33.3 isohaline. The green dots to the AZMP, so a longer time series in the model. This is sort of the recent period after the spin up. But you can see the inshore components, again, that isohaline's moving offshore, more volume transport, and significant increase in the freshwater transport with time. Again, looking at the green is the OBS, the red is the model. They're falling in the same range. So there seems to be some good consistency model and observations. If we go to the 34.8, so that's all the fresh water in the signal, so going beyond the end of the observational sections. The volume transport hasn't much changed, that's staying consistent, but because you've got that so much more fresh water, you've had significant increases in fresh water, and the numbers are quite significant. Most of this exchange occurs down in the southern part of the Grand Banks, as the animation showed. The interesting, farther north, there is some offshore exchange in summer driven by Ekman processes, with it then going back onshore the rest of the season. And as that's associated with, if we look at the Ekman, the winds change in the sort of the summer, there's Ekman transport offshore, other seasons it's onshore. So there's only one region where the winds are potentially playing a role in driving offshore. Otherwise it's the eddies in the smaller scale process. And in those regions where you do have offshore Ekman transport, that is playing a significant role in the exchange. By Flemish Cap, and now I've got some of the error bars, you can really see there's a lot less freshwater transport. A lot of it has gone offshore, most of it bound by it before the Southeast Grand Banks, but some of it does go around to the Scotian Shelf. And a lot of it's related, and the larger numbers relate to the Arctic output, but also at 160th, that Pouneh was showing, we've got those eddies going offshore, but 160th can represent the coastal or inshore currents. And so what we see, what surprised me compared to all the lower resolution models, is even though you have freshwater exchange into the interior, the freshwater transport of the West Greenland Current does not decrease at the same time, because it's being fed by the coastal current that's only represented at 160, and that means there's significant fresh water in the West Greenland Current that can go to Baffin Bay and all the way around to the Labrador Current and remain on the shelf and remain, I think, all the way to the Grand Banks, missing some of the convection region. So as a summary, we've used 1/60th. The model TS and sea ice fields and transports compare well with the observations. The isohaline with the low salinity waters moving offshore, freshwater transports increasing, significant offshore exchange around the Flemish Cap and Grand Banks. And because this 1/60th Labrador Sea's been interesting, we're now playing with running the entire Arctic Ocean at 1/60th. So I know I've had lots of stuff and talk quickly, but I've tried to cover some interesting behavior on the Labrador Current in our simulations.
Thank you, Paul. I'm going to grab the first question again. So I was trying to look at the green points by themselves, the observations by themselves, and in some cases, they didn't seem to have the same trend as the model. Do you the way you were talking, you think that is lack of temporal resolution of the observations, correct?
Let me just pull that up. So if I, this is a good question, whether it's the, sorry, I just stopped showing it. That's one of the concerns is that the sections only for 33.3 isohaline contained. If I want to compute it for 34.8, which is the typical one, that goes beyond the end of the observational section. So you're missing a component of the transport, and especially as showed with the isohalines, that the freshwater going in more and more offshore, I'm worried about that over recent years missing that component. That said, maybe the model is overestimating that. It can always do so. That's a good question, and that's what, as we try to finalize this analysis, that's one thing I really want to look at further.
Okay, there's a question now in the chat from Nancy. Very nice talks, Paul and Pouneh. Have you also looked at exchange of slope water onto the Labrador shelf?
It's on the list to do. It has not been completed yet. Pouneh should be looking at it when we deal with those eddies in that exchange. That's the problem with high resolution models. You get more and more output and more things you want to look at and no more time.
Less time.
Less time, exactly, no more time, yeah.
Do we have any further questions for Paul? Yes, from Gochi. How well does the 1/60th model reproduce the cold intermediate layer over the Grand Banks?
Good question. It is, when I showed the TS plot comparison, it does a decent job. That said, it's not quite as cold. I would say it's a 0.4 degree or something warmer, and it's maybe a little thinner, so it's there, but there's obviously things that can be improved.
Okay, thank you. Give it a few more seconds, see if we get another question coming in, but otherwise, thank you, Paul. And we can start to move to our next speaker. And so Drew Peterson is going to talk about quantification of constrained scales with an ensemble analysis. And we are a little ahead of time, Drew, so take your time.
Yeah, okay. Well, now I'm having trouble finding my screen sharing here, but a second. 1, 2, yes, no, I got 2 screens. Share the screen. Oh, wait a second, here we go. There we go. It was staring right at me, right in the face.
Okay, you are not in full screen mode
No,
yet.
no, I'm not in full screen yet. No, well, let me go into full screen. Come on. Stop the share for a second and do it. Oh man, sorry, I'm gonna use up all my spare time, aren't I?
Yeah,
we
that's
did-
fine.
We did try this and it worked fine.
Yes.
What did I do wrong? What did I do differently? Oh man, okay. You may have to go with the. Okay, I'm still on full screen. Oh,
We're not seeing anything right now.
yeah. Whatever I did last second, it worked finally. Now you're
Okay.
seeing full screen,
You're not
correct?
sharing yet. You're not sharing with us.
I'll share with you guys.
That would
Share.
be nice. Yeah, we'd like to be shared.
Yeah.
Excellent.
Excellent.
go, Drew.
Okay. Thank you. Okay, so yeah, I'll be talking about constraint scales with an ensemble analysis. Now I have to be able to, this is work I've done with Greg Smith and Kamal Shikar at Environment Canada and Andrea Storto with CNR in Italy. So first of all, why do we want to have an ensemble analysis? Well, this is from a paper we did shortly after implementing the coupled JEPS forecast model. And so we actually had sea ice and ocean output and our integrations into the 15-day ensemble forecast. And so this is an example from sea ice, where you can see that, I mean, the ensemble system does a better, well, this is a probabilistic observation. It's the probability of ice, so it's kind of a cheat that it's something that the ensemble should do better. But obviously, the red line here shows that the red solid line shows that the ensemble does a much better that job than the deterministic models at predicting probability of ice. Nonetheless, if you look at the spread in the system, the dashed line at the bottom of the screen there, it starts off at 0 and grows fairly slowly, whereas the air in the system actually grows quite quickly over the first 2 days. And the black line in that black horizontal line in that screen is a representation of the uncertainty in the actual observations. And so the uncertainty or the spread in the system is really very much an underestimate of the uncertainty in just what the observations in terms of what the sea ice cover should be. And so that plays a role into your forecast. So you have these large growth in errors over the first 2 days as basically the model is trying to accommodate that uncertainty in the observations that is there in all the instabilities in the model, but it's not actually represented in terms of the initial conditions. And so that's something we wanted to change. We wanted to essentially start putting some uncertainty in the initial conditions that would be representative of the uncertainty in the observations. And well, just to say that this is the same plot for the system that will go operational in a week time. Obviously, we still haven't put in this ensemble analysis yet, and so we're still getting very little spread, our slow growth in the spread. So this is something we want to change, and we're hoping to change it in the next innovation cycle, which will be in 2 or 3 years. Starting, and the race will be starting next week to get this all done. With about 2 years will go very quickly. So first of all, a quick summary of the GF system. So this is the global ensemble or global. Well, first of all, the quick word about the atmospheric equivalent to this. This is the global ensemble prediction system has an atmospheric data assimilation that is LATKF. They were the first center to implement that. So already the atmosphere has has baked into it the uncertainty in the initial conditions that is representative of uncertainties in airs in the atmosphere. So it'd be nice to have that in the ocean. So for the ocean right now, we have the GEOPS Ocean DA, the Global Ice Ocean Prediction System. The Ocean DA, and that is a version of the Mercator system, the simulation Mercator. SAM2. Another innovation that we're going towards in the next system is an update on that system. It's still going to be based on the Mercator system, but it's their new MROA system that basically has a separate a simulation system and observation operator system. And we're also building a new essentially suite to put this all into. And so we're going to have essentially a fairly new system already that uses these new these separate components that will make it very much easier to build an ensemble of that, because now all we have to do is create loops through these things, and it should all be hunky-dory and very easy to do. Moving on about our current system, it has a 7-day window that assimilates SST, sea surface height along track altimeters, and TNS profiles. And I think I'll skip the rest of it, but except for the fact that the atmospheric forcing is from the deterministic IAU step of the atmospheric assimilation system, or the deterministic atmospheric system. And the ocean model is NEMO. So in order to make this an ensemble system, well, we'll start with the GEOPS system. Instead of having a single external forcing with the GDPS atmospheric forcing, we can shove in the GEPS atmospheric forcing. I used, when I did the experimental trial of this, I used the 12 to 36 day forecast, sorry, 12 to 36 hour forecast, because that was the easiest set of fluxes to find and use. That's opposed to the GEOPS system, which actually, as I said, uses IAU level, or IAU time step, or IAU phase forces. So that is, and they found that was a better solution. So that's something we have to consider, whether or not we want to use forecast forcing versus analysis forcing, and what will be better for an ensemble system. But that's kicked down the road for a little bit. In addition to that, I've also added this Storto Stopack package, which is basically a stochastic package for the ocean that has stochastic parameter perturbations, stochastic parameter tendency perturbations, and a stochastic kinetic energy backscatter. Unfortunately, the last of those kind of ended up in producing some instabilities, and so we've kind of left it out of the mix for the time being. That's something I may return to in the future, but for right now, we just have the parameter perturbations and the perturbed tendency perturbations. And so moving on to the results right away, I was going to, this is a sea surface height current focused talk. I was going to throw in a slide on how it improves our profile fits as well. Unfortunately, I forgot to, so that means that you get to take my word that the ensemble system greatly improves your fits through the ensemble mean, greatly improves your fits to profile data. And that's particularly true in in eddy rich areas like the Antarctic circumpolar circulation. So that's a good plus for the system. So now moving on to the spread error relationship in sea surface height. On the left upper plot here is the root mean squared error between the altimeter observations and the model fields. On the right, upper right is the spread in the system. And while I've cheated, the contour intervals of the spread are 1/3 of the contour intervals of the root mean squared error. So it looks like they're basically almost a 1-to-1 representative of spread and error. Of course, the spread is considerably smaller at this point than the error, but but that error also includes error due to the observational error. It also includes bias, and you really should remove that. So the bottom left is the observational error. And so if we remove the bias and the observational error from the root mean squared error, and then look at that basically the difference between the spread and that error, you can see there are areas where it's overrepresentative, the blue areas, where mostly you had the observational error, but in the open ocean, it's probably the spread is under dispersive. It's not really doesn't have the amplitude to truly represent the uncertainty in the system. That's again something. So now the observational error in this case includes coastal error. It includes the instrument error, but the instrument error is actually quite small. It also includes coastal error and also representativity error, which is a little bit uncertain or it's really, that's the representativity error. Really, we do want the ensembles to represent, because basically the representativity error is saying, well, we have these observations here, but are they? I mean, how do you put them into a model where that observation, there's 150 kilometers between observations, and you have small scale eddies in that space, and so there's a certain representativity error due to the large scale structure of your observations, and that's kind of in this observational error. So long story short, if I remove the observation error from my estimation of the spread, then obviously I've got an under dispersive system that's all red in that lower plot there. So that brings me on to the thing that I'm going to spend hopefully the most of my time here, and that's constrained and unconstrained scales. So as I said, I mean, the data assimilation constrains certain scales. You have the observations. They are ocean observations are available now, but they're still very sparse and separated. And so really, the observation can only constrain the long scales. Of course, at the very high resolution, you don't represent the physics at all in your model, so that's completely unresolved by the system. But you have this big chunk in the middle where you're unconstrained by the observations, but you do model you do actually, that is represented in your model. And so in this case, it would be something like mesoscale eddies, which this is the eddy permitting model. So you do have some mesoscale eddies in it. They are not necessarily constrained by the data assimilation. They're there, but they're basically free. And so you have this unconstrained portion. And so the point of that is that if you have an ensemble, these unconstrained processes will be free, they'll be random. And so if you have an ensemble, if you look at the ensemble mean over that, then essentially you can remove the uncertainty due to those unconstrained observations, and get some more information.
1 minute.
1 minute. Oh, great. Okay. So power spectrum analysis. I've done a power spectrum analysis of the kinetic energy in the system. And the whole purpose of that is, so I've done a power spectrum analysis of the ensemble mean and a power spectrum analysis of individual members. You can see that there's a difference between these two. There's a lot more power in the members, less than the mean, but there's also, in that discrepancy grows at smaller timescales. And if you actually look at the ratio of the two, there's a definite minimum where you essentially your ensemble mean is filtering out data. And so I'm going to basically leave off with this one here, and that's essentially that one was based on basically doing it over the whole globe. I've done it in various different boxes throughout the world, throughout the globe, and as you can see that you tend to get much longer length scales near the equator than as you go out for the observation, and that's essentially Rossby radius dependent. You have Rossby radius. So you're basically able to filter out some of the uncertainty due to mesoscale eddies by having this ensemble system. And I'll briefly show this without any context. You can improve your fit to currents in the system, and leave it at that, I guess.
Thank you, Drew. I don't see a question yet in the chat. So I will ask a pretty standard question. How much more do you think you could improve the prediction system with ensembles compared to using the same computer power to reduce the resolution or improve your parameterizations?
Well, I think in some sense you can produce, but it all comes down to, I mean, we can crank up the to a higher resolution and get a much nicer solution that will have more processes in it. But as I said, a lot of those processes will not be constrained by the observations at all, so they'll be basically free in the model, and you won't know if those additional processes that you got from the high resolution are doing what the reality is doing, or if they're doing something completely different. And so in conjunction of having a high resolution system and having an ensemble system, you can get estimates of the uncertainty. You can figure out how uncertain are these unresolved or unconstrained processes in our system, and then you can go back to your high resolution system and say, well, this is the best answer we have, but there's still this uncertainty that the ensemble can only give us.
Thank
So
you,
you
Drew.
really need both.
Of course, you really need both.
And you always need both.
Yeah. So at this point, I'd like to thank all our speakers. I don't want to keep us long because they have definitely keep us on short breaks here. So this concludes this session for this session for this year. Thank you for all participating, and I will see you at the future sessions. And much appreciated to all our speakers. Thank you.
Thanks, Susan.
Thank you.
Thank you.
Thank you.
Thank you, Pouneh. Thanks, Drew. Thank you, Wendy. Well, it's not our session, it's switching. So I'm gonna leave. Yeah. Okay, so we'll pass it on to them. Bye for now.
Yes, oh, sure. Yeah. Great. Here's me. And another question is Nancy. Yes. What's your name, please? Wendy. Yeah. Thank you very much for the help. I, for sure. At the end of our session, we actually have a discussion part. I'm not sure it's allowed to, for all the participants to turn on their video to make contributions. Okay. Okay. So no, it's a discussion. We want to get input, input from the participants. Yeah. Yeah, it's not a question. It's more we want to hear people's opinion. In the last part, we are not a presentation. It's a more discussion part. So yeah. okay, we do have options, so we have